Let's start with what AI is. AI, or artificial intelligence, is a broad field concerned with building computer systems that can perform tasks normally require human-level intelligence, such as perceiving the environment, learning from data, reasoning about information, planning actions to achieve goals, solving complex problems, making decisions under uncertainty, and expressing themselves. There are two fundamental approaches to AI. The first is symbolic AI. Symbolic AI uses explicit rules and logical reasoning to make decisions. It works particularly well when the rules are clear and can be written down in advance. The second is data-driven AI. Instead of following predetermined rules, data-driven AI learns patterns from data. This approach is useful when writing all the rules by hand would be difficult or simply impractical. For example, consider an AI system that classifies an incoming email as either spam or not spam. A simple symbolic AI system might use the sender's email as a rule. If the email comes from a known spammer, it is marked as spam. A data-driven spam filter works differently. Instead of relying only on rules written by a person, it learns what spam looks like by examining a large number of emails. When a new email arrives, the system looks for patterns associated with spam. These might include particular words or phrases, the style of writing, or the overall tone of the message. If the new email contains patterns similar to those found in known spam messages, the system marks it as spam. In modern AI systems, symbolic AI and data-driven AI are often combined. A self-driving car, for example, might use data-driven AI to recognize road signs and symbolic AI to follow traffic rules. Data-driven AI can be divided further into two categories. The first is predictive AI. Predictive AI learns from data in order to predict something. We have already seen two examples. A spam filter predicts whether an email is spam, while a self-driving car predicts whether an object is a road sign, and if it is, which road sign it is. The second type is generative AI, and this is what this course is about. Generative AI produces new content based on its input. It can generate text, audio, images, video, molecules, or other types of content. One important type of generative AI is the large language model, or LLM. An LLM is designed to process and generate text. Let's break down the name large language model. The word model refers to a particular implementation of an AI system. The word large reflects the enormous amount of data used to train these models, as well as the large amount of memory needed to store the patterns that they have learned. And the word language tells us that these models focus on natural language, taking text as input and producing text as output. LLMs can answer questions, summarize articles, draft emails, explain concepts, and generate programming code. Some language models can also process visual information. These are known as visual language models, or VLMs. A VLM can answer questions about a diagram, explain a screenshot, or describe what it sees in an image. Other generative AI models can generate images or videos using text, images, or other visual information as input. You can use these models to create new images and videos or to edit existing ones. A common technique behind image and video generation is called diffusion. A diffusion model begins with random noise and gradually refines the noise into a coherent image. This process is fundamentally different from the way LLMs and VLMs work. But we will not explore the technical details in this course. The basic principle for using a diffusion model is similar to those for using other generative AI systems. Now that you know about different types of generative AI, let's zoom in on LLMs. The goal here is not to make you an LLM expert, but rather there are two reasons for understanding the basics. First, some of the limitations of LLMs arise directly from how they work under the hood, and you will explore these limitations in later units. Second, understanding how LLMs work will help you make informed decisions about which LLM model to use. To understand LLM, let's begin with a key term, the prompt. A prompt is the instruction or question that you gave to an LLM to guide its response. The process through which the LLM generates the response is called inference. Note here that the word inference does not mean logical deduction. In AI, inference simply means running a trained model to produce an output. Although LLMs receive text and produce text, they do not handle text in the same way that humans do. Computers work naturally with numbers. So, before an LLM can process text, the text is converted into a sequence of integers called tokens. A token is the basic unit of data processed by an LLM. The model's output is also produced as a sequence of tokens. These tokens are then converted back into readable text before the answer is shown to you. Here is one practical detail. On average, an English word uses roughly 1 to 1.5 tokens, while a Chinese character may use roughly 1.5 to 2 tokens, depending on the model. Understanding the concept of tokens matter, because many AI services measure usage in units of tokens, and they may also charge based on the number of tokens used. At a basic level, an LLM generates text by repeatedly predicting the most likely next token. It does not write the entire answer at once. Here is how the process works. The model first receives a sequence of input tokens containing your prompt and predict one token that could come next. That predicted token is then added to the existing input, and the model predicts the next token. The new token is added again, and the process repeats. This continues one token at a time until the response is complete. To make this process more concrete, let's walk through a simple example. For clarity, I will use words instead of tokens in the example. Let's suppose the input to LLM is NUS stands for the LLM might predict national as the most likely continuation. The word national is appended to the input, and the input then becomes NUS stands for the national. Based on this longer sequence, the model might predict university as the next possible continuation. The process continues one prediction at a time. In other words, an LLM produces what it considers the most plausible continuation based on patterns in its training data. Given it the input 1 plus 1 equals, and it is likely to produce 2. But it does not necessarily mean it is performing arithmetic in the same way that a calculator does. At its foundation, LLM is predicting a likely continuation. This brings us to the first and perhaps the most important fundamental limitations of LLMs. Producing the most plausible continuation can result in text that sounds fluent, confident, and convincing. But fluency does not guarantee truth. LLM can hallucinate. This means that they can produce statements that are factually incorrect, unsupported, or logically flawed, while still sounding completely natural. An LLM does not reason in exactly the same way that a human does. And by itself, it does not automatically consult an external knowledge base to verify every answer before responding. Another source of error comes from the token-based representation of text. Because LLMs process tokens rather than seeing every word as a simple sequence of individual letters, they have historically struggled with some basic character level tasks. A well-known example is asking how many letters R appear in the word strawberry, or how many letters P appear in the word Google. Some models have answered these questions incorrectly, even though the task seems trivial to a human. The information given to an LLM is not limited to your latest prompt. In a multi-turn conversation, some or all of the earlier messages may also be included as part of the input. And when you upload a document, its contents may be included as well. All of this information taken together is called the context. The context is everything the model has access to when producing its response. The context window is the maximum amount of information that a model can consider at one time. A large context window allows the model to work with more information, but it also requires more computation. Modern LLMs may support context windows ranging from around 128,000 tokens to 1 million tokens or more. For comparison, all 7 Harry Potter books together contain roughly 1.5 million tokens. The size of the context window is therefore an important consideration when choosing a model. it involves a trade-off between how much information the model can consider and the computational cost of processing that information. A limited context window also helps explain why an LLM may sometimes appear to forget something that you said earlier. In a very long conversation, older information may eventually fall outside the context window. And even when information is still inside the window, the model may miss important details that are buried within a large amount of text. Long conversation can also drift away from the original topic. Later instructions may conflict with earlier ones, and the model may become confused about which instruction to follow. The results can be responses that are inconsistent, incomplete, or no longer align with what you originally asked. Another important idea for understanding LLMs is the number of parameters. The number of parameters is often used as a measure of a model's size. A parameter is a numerical value that is adjusted while the model is being trained. You can think of parameters as dials, billions of them, that are tuned during training to help the model produce better outputs. In general, the more parameters a model has, the greater its capacity to learn complex patterns. Model size is usually described by the total number of parameters, whether that is millions, billions, or even trillions. These parameter values must be stored in the computer's memory. So, larger models generally require more memory and more computation to run. Some models distinguish between total number of parameters and active number of parameters. Total parameters describe the size of the entire model, while active parameters are the subset used to process a particular input. This means that the model may contain a very large number of parameters overall, but use only a portion of them for each response. By activating fewer parameters at a time, the model can reduce the computational cost of inference. However, bigger does not always mean better. A larger model often has greater capabilities, but size alone does not determine how useful a model will be. For a straightforward task, a smaller model may be faster, cheaper, more privacy-friendly, and simply good enough. So, how are all these parameter values determined? They are set through a training process that takes place before the model is released. The exact process varies between models, but it is useful to think of it as having three main stages. First, learning the language patterns. The model is trained on a very large collection of text and other data. Through this process, it learns general patterns in language, including how words, sentences, and ideas tend to relate to one another. Second, it is trained to follow instructions. The model is then fine-tuned so that it can respond more helpfully to instructions given by people. Third, learning what humans prefer. The model is further adjusted using human feedback about which responses are better. This stage is known as preference tuning. In other words, a chat model is not trained only to predict what text comes next. It is also trained to produce responses that people are more likely to find helpful, appropriate, and useful. Reference tuning, however, can introduce its own risk. People often prefer answers that sound confident, clear, and agreeable. As a result, an LLM may produce an answer that sounds highly confident even when that answer is wrong. It may also agree with the user even when the user is mistaken. This tendency to agree too readily is sometimes called sycophancy. You should be aware of these tendencies, especially when using LLMs for tasks where the consequences of an error may be serious. The training process can also be extended to give an LLM additional capabilities. Some LLMs are described as reasoning models. These models are trained to carry out a more extended process before producing a final answer. Product descriptions often refer to this process as thinking or planning. At this point, you might be wondering, didn't we just say that LLMs cannot reason? The key is to understand the distinction. A reasoning model is not the same as symbolic AI. Symbolic AI reasons by applying explicit logical rules. A reasoning LLM still generates plausible tokens one after another. However, before giving its final answer, it may generate intermediate steps, reconsidering earlier conclusions, revise its approach, or check whether the answer is consistent. This process may look like reasoning, but the model is not manipulating formal logical rules in the same way that a symbolic AI system does. Some LLMs are also trained to use tools. These tool-use models can interact with external software as part of producing a response. For example, a model may search an email inbox, check a calendar, or retrieve current weather information. We will explore tool use in more detail in later units. Now that you understand the basics of how LLMs work, let's consider how this knowledge should influence your choice of model. A model is not automatically better because it is newer, larger, or more expensive. Choosing a model involves a trade-off. On one side, there is the level of accuracy and capability that you expect. On the other, there are different forms of cost. These include the financial cost per token, the computational resources required, the speed of the response, and the possible implications for privacy. In academic and professional settings, using a model that is unnecessarily powerful can waste time, money, and energy. But using a model that is not powerful enough can also create problems. It may produce errors, shallow analyses, or answers that sound convincing without being reliable. So, the right question is not which model is the best. The question is which model is appropriate for this particular task. Let's look at 3 examples. Suppose you want to rewrite and polish a paragraph in an email. This is a relatively straightforward and low-stake task. A simple, general-purpose LLM will usually be sufficient. Now suppose you want an LLM to explain why your solution to a mathematical problem is wrong. This requires more careful analysis. For this task, you may want to choose a larger model with a stronger reasoning capability. Finally, suppose you want an LLM to read a long document and generate comprehension questions about it. In this case, the model needs to process a large amount of information at once. You should therefore choose a model with a sufficiently large context window. We have reached the end of Unit 1. Here is a recap. In this unit, we have learned about the major kinds of AI systems, including symbolic AI, data-driven AI, predictive AI, generative AI, and large language models. We have also learned key terminologies about LLMs and how they operate at a conceptual level, and how this leads to fundamental risks such as hallucination, overconfidence, and a tendency to agree with the user even when the user is wrong. In the next few units, we will explore how to improve the quality of LLM outputs through better prompt and context design, as well as how to build workflows that thoughtfully divide the responsibilities between humans and AI.